I do. So who in the room has ever used an HSM? No? Okay. Who recognizes this room, the red curtains, the floor? No, you're too young for Twin Peaks, I guess. Alright, so who am I? Quickly, I'm JP. Hello. I've been doing crypto security for quite a bit. My specialty is cryptography, not cryptocurrency. I hate cryptocurrency, even though my company is kind of in that space. I don't like to brag, but this is a very good book if you like cryptography. I'm in a company called Taurus, co-founded in 2018. What we do is technology for banks to issue and manage tokenized security, so stable coins, cryptocurrency, and all that stuff. So I'm here with a colleague of mine, Bina, who's here. And we're not in the crazy, unregulated criminal cryptocurrency business. We are a regulated financial firm, audit every other week, so, we're good guys. Okay, so let's talk about HSMs. What's an HSMs in the first place? Is it a hardware security module, or is it a hardware security module? It's a bit of both, as you'll see. So, agenda and so on. Small disclaimer, there's many different HSMs on the market. We haven't used every single one. Actually, we only use HSMs from one manufacturer. So if you know, you will see, not dropping names. But what we say may or may not apply to your favorite HSMs. But if you haven't used HSMs, apparently you don't have any favorite HSM. So we already did that. And now let's move to, definition of an HSM. So if you go to a vendor's website, they might say it's a dedicated crypto processor that is specifically designed for the protection of the crypto key lifecycle. Oh my God, you're even more confused now, right? Crypto processor. So crypto is not cryptocurrency again. It's cryptography, encryption, signature, all that stuff. Processor, a system that processes stuff, that, has an input and gives you an output, and also stores stuff. Specifically designed, we understand. The protection means confidentiality and integrity, and availability to some extent. And the crypto key lifecycle is the lifecycle from the like our life, from the moment we're born to the moment we ultimately die. So the keys is the same. They're just, small life beings. They're generated. They're stored somewhere. They live. They do stuff. They do good stuff. They do bad stuff. Maybe they are rotated. They're removed because they're not doing a good job. Maybe they're getting too old, so they retire. And then ultimately they're deleted and goodbye. So here's how it looks. Typically, you might, see HSMs as, one rack unit boxes like that. A big box, and people will call that an HSM, even though technically what's the hardware security module is the small piece inside that is doing that stuff I mentioned. Oh my God, what did I do? Oh no. Okay. On the right hand, it's a PCI Express form factor, HSM. So it's kind of equivalent form factor. These ones are connected to the network, and this one's just to the PCI Express. And you also have small USB form factor HSMs as well. So why would you use an HSM? Why would you worry about buying such a box, which is quite expensive, admittedly? So the whole point is to store secret stuff and to keep that stuff secret. So secret, we mean secret keys, private keys. What do you do with private keys and secret keys? Well, you sign stuff, you decrypt stuff, and you might encrypt stuff if you're in a symmetric key world. Here MAC is message authentication code. It's kind of signature where you have the same key on the two sides. So you can admire my drawing skills here. It can work as follows. It can be very basic. You send a request to the HSM. Hello, HSM. You have this key K. I have this message. I send you the message, and you send me the signature of the message with the key K. I don't receive the key. The key stays in the box. It stays in the secure box. The HSM is computing the signature, and I get to learn the signature. So here you might say, oh, that's cool, but if everybody can do that, if everybody can use the key, then what's the point? So you need some access control. We'll get there. The whole point of an HSM, if your company, is if all your computers, mobile phones, doors, fridges are compromised, then the attacker will not be able to extract the key, which is super secret. And if you lose the key, you die. So you put it in a very secure box. And even if all of, Russia, Mossad, CIA is in the organization, well, these guys might be able to do it, but in different ways. But if a purely remote network attacker has compromised all your virtual machine, hypervisors, Kubernetes, they should not be able to get their hand on that key. That's theory, and in security it's always complicated. So why we would do that? When do we have keys of high value? Well, blockchain, of course, you know how it is. You lose the key, you lose the money, they steal the key, they steal the money. If you're an individual with like 100 francs, dollars, euros, you don't want an HSM, you don't need that stuff. But if you're a bank and manage literally billions worth of Bitcoin or whatever is your favorite currency, then you want to be very careful. You want to buy one of these boxes. Code signing as well. Okay, some of you probably know the Microsoft world, whereby you create an application if you want it to be signed. You want it to be recognized by Microsoft Windows without having the pop-up, malware. You need an HSM to sign your binaries, to sign your installer and whatnot. Sometimes database encryption, even though what you have in the HSM is not the actual encryption key, but a key encryption key. And last but not least, PKI, public infrastructure, certificate authorities, where the private key could allow you to compromise, every single website on the planet, like Google, IBM, and whatnot. So you want this private key to remain private because you don't want to be able to forge certificate, to forge signing certificate, and so on. Okay, how do you talk to an HSM? Do you just, send a letter? No, it works with computers, networks, PCI Express, USB, TCP IP. As usual, nothing new here. I will skip. Okay, security. Some butter from me, I guess. I'll let you breathe as well. So, the S in HSM is for security, so we do have security feature inside, and, bear with me, there's a lot of stuff. Not saying everything is good, but there's a lot of stuff. First of all, you can share your HSM with your friends. Well, if you have friends, and if you have an HSM. You have this concept of partitions. Think of it like user accounts with different isolated memory spaces to store your stuff, to do whatever you want, but sharing the hardware, Spectre meltdown, set channel, etc. This is sometimes called partitions. And so you have a partition that is for you, so you have your credentials. For each partition has their partition security officer. So for each partition, you may have different types of users with different types of capabilities. RBAC, role-based access control. So you have different roles, admins, users, and other stuff that have different capabilities. Like this guy might be able to update the firmware. This account might be able to change the password of this other guy. This guy might be able to add new cryptographic objects in the HSM. So like add a key. This other guy might be able to create a certificate and declare it as trusted. So I'm not going to go into the details. It's quite hairy, but it's quite hairy. There's a lot of stuff that can go wrong as well if you don't configure it correctly. Of course, that's the problem with security. PKCS 11, who already heard of that? Okay, trust me, you don't want to. No, don't go to internet, don't open the specification, you will hate me for that. It's terrible, it's horrendous. It's C-like syntax, but it's extremely important. It's the way you communicate with hardware tokens, with hardware stuff that does crypto. It's the way you format messages, where you put each bit, what this bit means, how it's interpreted. So when you talk to the HSM, you have your client code, and you can use the same client code for every single HSM because they all talk the same lingua franca, which is called PKCS 11. So PKCS means public key, crypto, something. Yeah. But yeah, if you don't need that, you can get on with your life. You don't need it. Last but not least, FIPS, so the federal US line of standards, and 140-2 and now 140-3 is about physical security, temper evidence, temper protection, and to some extent temper resistance. What it just means is that you get some guarantee that if someone, let's say that's an HSM, if you get your hand on the HSM, you can just open the box and, put a sensor and just dump the memory. You have a bunch of security controls. Like if you have your HSM and you kick it, it will not like it, it will reset and zeroize all your keys. If you plug the power, in some ways, I don't remember what we did, but sometimes we're not really nice with the HSM and it didn't like it and it reset. And if you try to open the enclosure, likewise, it will detect it and say, oops, no, sorry, I forget everything. That's an interesting way of operating. And it also guarantees you that the built-in cryptography is correct according to the NIST FIPS standard, like AES, ECDSA, and so on. However, so if you've been doing software security exploitation, ASLR is everywhere. Oh, your exploit works without ASLR. Who cares? Well, welcome to the 90s. The HSMs often don't have any ASLR or DEP, so no exploit mitigation. Maybe the reasoning is, people won't try to exploit this in the first place. The attack surface is so strong, so who cares about? It just there's a lot of legacy code and, There might not be remote attestation. So remote attestation means you get the response, but you get a cryptographic guarantee that the response actually comes from a certain program. So it's quite difficult to put in place. It's the strongest guarantee you can have. Because if you receive a response, you say, okay, but how I'm sure that the code they run was this exact piece of code, which I've been verifying with my, suite of tools. You can do it, as I will show later, but it needs some hacking. Now, what's inside? You might find a board with electronic component, some PowerPC chip. There might be some ARM, there might be some other stuff, but the ones we work with, they tend to have PowerPC, so, big endian and whatnot. Some crypto accelerator. So crypto accelerator, what it means on the system on chip, you have some hardware silicon, so not FPGA, but really hard-coded. But you might have FPGAs, but the whole point of this crypto accelerator is to accelerate crypto to make it faster. Sometimes I wonder if it's really faster because it's super slow, but no, the interesting thing is that when it's in silicon, you can't patch it. If it's an FPGA, you can patch it. If in software, you can patch it too. There's typically some Linux. I've seen some stuff with OpenBSD, but most of the time it's Linux. And you have a bootloader, which may or may not be secure, how bootloaders are. And there's crypto software libraries. When I was young and naive and even more stupid than now, I saw that in hardware security modules, all the crypto was in hardware. I was like, so cool, strong crypto, hardware defenses and whatnot. Well, if you look up on the open source credits, they use OpenSSL, they use the Linux kernel, they use OpenSSH, the same stuff that everybody uses. So the hardware security doesn't mean that everything is done in hardware. So don't think like me. And there's a firmware, so the operating system of the appliance. It can be updated. The updates are signed. Sometimes they might even be encrypted. But if you see that's once encrypted, you can maybe look in the past and see if 2 years ago it was also encrypted. And you can do other stuff. What crypto is it doing? So all the boring crypto that everybody does, elliptic curve signature, elliptic curve Diffie-Hellman, encryption, decryption, AES, all the FIPS suite, essentially. And very important, there's a true random number generator. So true just means, it's nothing fancy, it just means that it's not deterministic. It takes entropy from the analog world, for the temperature of the room, from the, whatever you can't predict, and feeds it into a DRBG, deterministic pseudo-random generator, that gets you unpredictable random bits that you can use to generate keys. And if this sucks, then you're dead. It doesn't matter if you use an HSM or not. If the randomness sucks, then all your crypto is dead and breakable. So, single point of failure and so on. Very important thing, and for the rest of this talk. So you buy an HSM and you can send its request to sign and decrypt. But you can't really customize it. You can't run your own, you cannot run your own games. You cannot run Doom on the HSM. You cannot add your email server. But some HSMs allow you to extend the firmware with some custom software module. So when you will send a message to the HSM, it will first be received by your custom module. And then you can run your own code in the HSM, which is pretty cool because you get a guarantee of integrity that other people will not be able to modify your code because it's been signed, it's in the HSM. It will not be modified, and guarantee of confidentiality because whatever happens in the HSM stays in the HSM. So it will replace essentially the init function of the HSM. You can add your own stuff. It has to be developed in C, the C language, boring C99. People don't like C, but I love C. There's the SDK of the vendor. But you cannot run, your huge, Kubernetes cluster or SQL database. It's limited to 8 megabytes. But it can do essentially pretty much everything that the firmware itself can do. It can talk to PKCS11 objects. It can access all the crypto primitives. So it's pretty cool. Okay. Now how can you make the HSM a bit smarter, a bit more resistant to attacks, defense in depth and that kind of stuff? Because the obvious problem, the elephant in the room is that, you might use an HSM, but if someone compromises your laptop and gets the keys, the pins, the password to use the HSM, and they can sign whatever they want, and then it's just security theater. So how do you deal with that? And also PKCS11, I told you, it's a piece of something, and there's some implementation flaws occasionally, and there's also some design limitations that, some gotchas that you really need to know, and you can shoot yourself in the feet. So you can look up this advisory about the UB keys. There was some news about UB keys recently. There was a paper by the Ledger guys in 2019 about HSMs, and they found some pretty scary stuff. So there's tons of things that can go wrong. Now, the last few days, everybody's like, supply chain attacks and, S-bombs and all that stuff. And you saw before that there's Linux. There's a bootloader, an open source bootloader. There's OpenSSL libraries. There are protocol buffers, all the standard stack, so to speak. But, firmware updates, they're like every 2 months, every 6 months. And it takes a while to get it FIPS certified again. They might not have the latest version. They might actually have very old versions. Very old, like 5 years old, So you can look up the internet, see, okay, you have this OpenSSH version from 3 years old. How many high severity CVs do we have here? And also what worries me, what I know will happen someday, publicly, is what I call cross-slot attack, cross-partitions. Because if you share the same hardware by 2 software isolated components, inevitably by the laws of physics, you will have leaks depending on what you do. So you will find a way to extract keys if the enclave or the partition 1 is doing one thing, the partition 2 is doing another thing. There will, of course, be side channel leaks. So you have to be careful to what you do. You have to be careful to what you do on different slots. And that's why many of our clients are like, no, we prefer our own HSM. We don't want to share an HSM with other guys we don't know. Supply chain issues, I told you, you can run your own code in the HSM. Yeah, very cool. But if Janta or some random people can backdoor your code, then they have root access on your HSM. And that's not a good news. Well, not for you. And of course, the random number generator issues. So I'm always scared when I see a black box RNG, when I see a box telling us, don't worry, we have a good RNG. But, Roca, a couple of years ago, this Infineon chips, they were found to be vulnerable because they tried to optimize the RSA key generation. It was optimized. It was much faster, but it was much less secure. Now, what about custom modules? Tons of things can go wrong. We found a lot of weird bugs, and, you have a file system, and if you put a slash in a name, for whatever reason, at some point it would crash. Like, okay, interesting. We had the case, I don't know if I mentioned it. Yeah, if you log too much, there's logs, but if you log too fast, it will not like it. Maybe the I/O is freaking out, so it might crash. Also, what we find quite early on, if you log a line that was more than 80 characters, it will also crash. But not gracefully, sick fault. And also the crypto interface, something that works on one version may not work on the next version of the HSM because maybe they made some different design choices that they did not document. And sometimes you have documentation, you're like, yeah, you read the documentation, you do exactly what's in the documentation. It doesn't work. You have to be more creative and find something else. But I guess it's the same for many lines of product. Okay. Hardening. How much time we have? Like 10 minutes? 15? Okay. That'll be fine. Okay. Hardening. That's really important. If you've been using HSM all your life, this might be boring to you, but if it's not the case, that will be potentially very useful. I will talk a bit about cloud HSMs at the very end of the talk. So I told you that PKCS11 can be, annoying, but you can filter the requests. You don't, instead of directly exposing the PKCS11, you can sit in the middle, receive the inputs, and add your own validation, parsing, whitelisting, whatever you want to do, or just block it altogether. So if you don't use an API or function, why expose it in the first place? Just ditch it. And it saved us, I think a couple of years ago there was a bug in one of these functions, and we didn't use it, we blocked it, and it was not exploitable. Also vendors can be created, they add their own extensions to this PKCSS event interface. Of course, because you can. What I found really cool, so in an HSM you have a lot of attributes. When you add a private key, when you add a secret in the HSM, you can tell the HSM, okay, this key can be used for signing, this key can be used for encryption, this key can be used for decryption, this key can be used for whatever else. So you want to put the permissions to give the least privilege. If this key is only to be used for signing, you only authorize it for signing. And likewise, you can authorize keys to be extracted, exported, wrapped. So you want to be as tight as possible. So on the right hand, you see these attributes. That's the PKCS syntax, CKA, something, value, sensitive, private, modifiable, blah, 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 blah. And to do that, you have to understand what each of these mean. It's not always straightforward. So, I mean, that's basic IT hygiene, but sometimes people don't have time or don't know that they can do it. So if you have a custom module inside, you can say, no, I refuse to work if I'm not in a safe space, if I'm not with the right attributes I want, if I don't have the right label on this key, and so on and so on. Okay. I told you HSM are for crypto, but you can run other stuff. You can put your software. It's Turing complete. You can do what the hell you want. So if you want to put business logic such as, oh, I will only sign messages that start with 0xAB3, you can do it. If you say, I receive a request, but I want it to be signed by a guy with this public key, you can also do it. You can say actually what we do when we receive a request to avoid a single point of failure. Say, okay, we only accept to sign this blockchain transaction request if your message is approved, signed by 3 out of 5 of these public keys that I know and I have in my HSM. It may not be clear, I repeat. So it's this quorum 3 out of 5, for example, validation, whereby you receive a request, please create a blockchain transaction to send 2 Bitcoin to this address. So it's not yet the blockchain transaction, it's just the request. I want to do this. But this request has to be cryptographically signed by a number of parties, and their public keys, their identities are hard-coded in the HSM. So you kind of simulate, what blockchain people call multi-signatures or multi-party something or threshold signatures, but purely in the secure environment of the HSM. And what is great is that it's completely agnostic of the blockchain, because you receive a request and you don't care whether it's for Solana, Bitcoin, Ether, or whatnot. And people who see the blockchain as a public database, they don't know that this happened under the hood. So, privacy and so on. But of course, if you use a custom module, if you get a remote code execution in the HSM, then you win. But you cannot get an LP privilege escalation. Can you guess why? You cannot escalate to root if you are already root. Yeah. So it runs as root. Yeah. That's not fun. So this leads us to role-based access control. You can implement your own, layers of roles. You can have different layers of admin. For example, what we do, we receive a request to sign something, and it has to follow certain patterns, certain roles, like, for example, the amount is limited to that, the address has to be whitelisted, and you create a number of roles, but the roles might have to change, so you cannot hard-code the roles in the HSM. So you're going to receive roles signed by admins, and you will verify the roles using the public keys of the admins, which are in the HSM. So there's a lot of keys, a lot of parties, it's kind of becoming a headache. But the upshot is that you can do quite complex stuff in this small 8 megabytes. Okay. Boom. something that I like. So you're familiar with the concept of end-to-end encryption. So end-to-end encryption is from the consumer from the producer to the consumer. So the textbook example is, messaging. So Signal, WhatsApp, they're end-to-end because I send you a message. It goes through a number of servers of WhatsApp and whatnot. It ends up on your device. Your device decrypts it. I want you to read my message. I don't want anyone else to read it. So only you can decrypt it. That's producer to consumer. If you look at Telegram, you send your message to Pavel Durov, to his servers in Dubai. Everybody and their dog can see it, you know who. And then Telegram say, okay, I'm going to forward it to the recipient. But they have this huge database of all the messages of everyone. Yes, but the UX is so cool. Okay, so you can do end-to-end encryption in your HSM because typically you may not talk directly, you talk via a gateway, bastion host. So you really want to implement producer to consumer encryption in both ways. And you can do that. Okay, sure. One important guideline is, at least from my philosophy, is I don't want to use software components that I cannot see, inspect, analyze. Really don't like black boxes because if you do a black box, if you have no accountability, then you can do what the hell you want and put backdoors. And there's been a lot. So you may want to minimize the usage of the black box components from the HSM firmware and instead use your own piece of software. Yeah. Especially, for the PRNG, you don't have much choice for the true RNG, for the entropy, but you can add on top of it your own DRBG. Okay, I will skip that part because it's quite complicated and it's very short anyway. At Black Hat, we presented that. Although the point is that, we have multiple redundant HSMs. They are stateless, but sometimes you would like some statefulness, for, anti-downgrade, for certain stuff. But you can't store a lot of data. So what do we use? When you have this kind of problem, you use trees, Merkle trees, and we actually use something called red-black trees for our specific problem. So look it up online. It's on my website. Okay, to conclude, the best practice, yeah, update your software, tighten the PKCS11 attributes, like I mentioned before. There's something called secure channel, which is not enabled by default. So secure channel is some kind of secure channel between the HSM and you as the first degree connection, not necessarily the consumer. It may or may not be completely secure. It used to be basic anonymous Diffie-Hellman, so not really great, but it's better than nothing, I guess. Minimize dependency if you add custom code. And if you have the dependencies, you need to, hardcode them, vendor them in your GitHub project. Don't pull dependencies from some random people on the internet. I mean, we're not NPM. Okay, access control, key management, blah, 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 blah. Cloud HSMs. Okay, you have a question. Can we do all that stuff with Cloud HSM? The answer is no, sorry. Because the Cloud HSMs, they're managed by the cloud provider. You don't have root access on it. You typically share the HSM with other people you don't know. You cannot run your custom software. You can custom software module on the Cloud HSMs. There's one provider. They allow you to bring your own HSM in the data centers, but then it's still your HSM. So you go back to square one. And also, it depends what you're up to, of course, but it's hard to get a guarantee that the HSM you talk to, the Cloud HSM you talk to, is an actual HSM. So there's some ways, some vendors give you some way, PKI, YC to do it. But I still find it a bit scary and a bit like, okay, I just want to say I use an HSM, I use the Cloud HSM. Okay, so let me conclude with that. So HSMs and in HSM software is very powerful, but, more power, more time to do stuff, more responsibilities, and more code to review, and maybe more headaches at the end of the day. So you need people to maintain all that stuff. You need to be very, very careful with the SDLC. So what we do, for example, when we build our custom module, okay, that's very important. That's the last thing I will say. When we build the software we put in the HSM, we don't build it on a laptop. Well, just, by myself. We have an auditor in the room. We have a specific laptop for that. We have a specific Docker container for that was created with the auditor with only the minimal stuff. And we make reproducible builds. And we get a certificate that this binary was built from a given version of the code. and we give it to client, and the certificate is done by an external auditor. And the certificate is also tamper-proof because it's signed by the Swiss Federal Confederation Authority. So it's not completely perfect, but it's putting the bar pretty high, and that's all I will say, and I thank you very much for your attention.